Okay, thank you very much for the introduction. And as you can see, the title of my presentation is Characteristic Dome Shape of the Critical Temperature at the interface between lanthanum aluminide and strontium titanide. And I'm going to present you our theoretical model, which is able to explain this characteristic shape of the critical temperature. This work was done in cooperation with Michał Zagrodnik and Michał Nowak from our university. Here you can find a very short outline of my presentation. I'm going to start with the motivation for our study, and then I will present our theoretical model and then results, and I will try to compare our results with recent experimental data. So first of all, let me introduce the physical system. So in our paper, in our presentation, in fact, we consider the interface between strontium titanide and aluminum and lanthanum aluminides. And here, in fact, between these two bulk insulators, the two-dimensional gas is created due to the polar discontinuity and the corresponding charge transfer to the interfacial region. So here we have, between these two materials, here we have a very narrow quantum well in which the electrons are confined, in fact. And we know from the DFT theory and from the experimental data that the electronic structure here is described very well by d orbitals of titanium ions. Sorry. And from this DFT calculations, we know that the situation is just a little bit changed than in strontium titanide in bulk form, because in strontium titanide we know that the d orbitals are degenerate, and here this degeneracy is lifted by the confinement, and we can see that the dxy orbital is shifted in energy just a little bit by about 50 millielectron volts. And we know from the literature that this system, this two-dimensional electron gas, is characterized by very interesting properties. Inter alia, it is characterized by the huge spin-orbit interaction. We can observe their ferroelectricity, magnetism, superconductivity, and also the coexistence between superconductivity and magnetism. And moreover, we can just control all of them by the gate voltage. Here we can just apply the gate voltage and control the electron concentration in this two-dimensional electron gas. So here in this presentation, I'm going to talk about the superconductivity. Superconductivity in this system was discovered many, many years ago. And here you have just experimental results from one of the most important and one of the first paper from 2012. And you can see that the system exhibits a very characteristic shape in the form of dome. Here you have the critical temperature as a function of the gate voltage. And in my opinion, the superconductivity in this system is still insufficiently explored because we still don't know how is the pairing mechanism in this system, and we are not able to understand this characteristic shape. For example, in the literature, you can find a few possible explanations. One of them is based on the electronic correlations. Another one says that probably this characteristic shape results from the strong pair breaking effect in dirty living related to the repulsive interband interaction. And another theory says that it could be an effect of non-trivial link between spin-orbit coupling and superconductivity. In this presentation, I will show you that, in fact, this characteristic shape can be induced by the specific symmetry of the gaps. Because let's assume that we have a very simple system with the Fermi surface given by a cycle. So we have a parabolic band here, but the symmetry of the gap is extended S-wave symmetry. So it means that the gap is momentum dependent. And we see here that it is given by this formula where gamma is a symmetry factor depends on the cosine function. So here you have a plot of this symmetry factor, and you can see that along this gray lines here, 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 you know, the symmetry factor is equal to 0. So if we, for example, if we change the chemical potential and we start from here near the Lifshitz transition, the Fermi energy is a very small cycle. So here we are here at the Kx and Ky position 0, 0. But here the symmetry factor is equal to 1. So it means that we have a very low density of states, but the superconductivity is induced because the symmetry factor is equal to 1. But however, if we increase the chemical potential, okay, this Fermi surface becomes bigger and bigger, and it starts to be close to these gray lines where the symmetry factor is equal to 0. So it means that from some point here, we should observe decrease of the critical temperature. And now the question is, how can we apply this very simple model to our system and just to explain this characteristic dome of the critical temperature in STOLAO? So our theoretical model is described by the Hamiltonian, which consists of 3 parts. Here we have a tie-binding approximation, repulsive Coulomb interaction, and here we have a part responsible for superconductivity. This TBA Hamiltonian is given by 3 terms. The first one is a single electron Hamiltonian, and here we have 2 parts related with spin-orbit interaction, but at the beginning we can just neglect both these terms. So here you have the Hamiltonian. I'm not going into details, but if you look at the electronic structure, you can see that indeed the XY band is located just a little bit in energy, just a little bit lower than the rest of bands here. So of course we also included into account the repulsive Coulomb interaction. Here we have the repulsive interaction on site, and also the interorbital repulsive interaction between electrons from different bands. And we included in our system superconducting pairing by this Hamiltonian. So we have a pairing between nearest neighbors here, 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 and here. So here is the Hamiltonian responsible for the pairing, and here we have also Cooper pair hopping, but the J prime parameter is 1 order of magnitude smaller than J. And of course, we were able to solve this problem, and we distinguish between, of course, energy gap in different bands, and also with different symmetry. Here we have an extended S-wave symmetry here, and also the D-wave symmetry. Here you have the symmetry factors for both considered symmetries. Okay. So if you look at at our results, you can see that in fact we were able to reproduce exactly the experimental data. So here you can see that the superconductivity in this system is induced mainly by pairing in these higher line bands XZ and YZ in the extended S-wave symmetry of the gap. Of course, we also have a component of D symmetry, but it is much smaller than this extended S-wave symmetry of the gap. And we also calculated this energy gap as a function of temperature. And you can see here you have for two different symmetries, and you can see that the correspondence between the experiment here and the theory here is very, very well. Okay, and of course this unusual dome shape of the critical temperature can be in this case also explained as some kind of interplay between the topology of the Fermi surface. Here you have a Fermi surface, and in fact the symmetry of the gap exactly in the same manner I showed you, I know, 2 slides ago. In our model, of course, in the next step, we also did calculations with the spin-orbit coupling, and you can see that the inclusion of the spin-orbit coupling does not change too much this figure. So we can see that for sure the link between spin-orbit coupling and superconductivity is not so important, is not able solely just to induce this characteristic shape. Moreover, in our model, we use two different methods of calculation. The first one is a normal, simple mean field theory, Hartree-Fock approximation. And the second was Gutzwiller approximation. And by this Gutzwiller approximation, we were able to include into account electronic correlations. And you can see that, in fact, we do not any difference between mean field theory and Gutzwiller approximation. So it means that electronic correlations do not an important role in the generation of this characteristic shape. Moreover, by the inclusion of the Coulomb repulsion, we were also able to reproduce the experimental data. Here you can see experimental data and the characteristic change of the monotonicity at the Lifshitz transition here, and this change of the monotonicity was also observed in our calculations. So it seems that our theory works, but we should also compare our theory to the existing one. There is one theory which was described in this paper in PRL in 2018, and this theory is strongly based on the experimental paper from 2012. Because in this paper, the authors wrote that, in fact, probably the maximum of the critical temperature here is related with the Lifshitz transition. Because, of course, if we change the gate voltage, at some point we should observe that the higher lying band here crosses the Fermi energy. So it means that we have a Lifshitz transition. And the authors wrote that probably the maximum of the critical temperature is exactly at the Lifshitz transition. So this theory says that it is possible, of course, just to obtain this characteristic shape, because, for example, if the chemical potential is located somewhere here, okay, so we are at this graph, we are here, so the superconductivity is induced in the lower lying band here. This is the band dxy, and we have a superconductivity. Then, if the chemical potential increases, we have a Lifshitz transition. And if we assume that in our model there is a repulsive interbutt interaction, so it could happen that this repulsive interbutt interaction will be dominant. It could be dominant. So it means that after the Lifshitz transition, in some cases we can observe decrease of the critical temperature as a function of gate voltage. However, if you look at different experimental results, you can see that the conclusions about the position of the Lifshitz transition exactly at the maximum of the critical temperature is still under debate. There is no common consensus that the Lifshitz transition should be exactly at the maximum of the critical temperature. Because if you look at this paper, for example, also from 2012, you can see here you have results from whole measurements, and you can see that the population of the higher lying band appears around the zero gate voltage. So the Lifshitz transition is somewhere here, but the maximum of the critical temperature is for higher gate voltage. And the same situation is observed here. Here you can clearly see that the Lifshitz transition, which is denoted here, is exactly at the beginning of superconductivity. But the maximum of superconductivity, the maximum of the critical temperature is located for higher gate voltage. In this paper, the authors even wrote that probably the superconductivity is not related to the lower line XY band, but for this superconductivity, this superconductivity is induced by the higher lying bands dxz and dyz. And if you look at the results from our theory, you can see that it's exactly what we have in our theory. In our theory, if the chemical potential is located here, so we have an occupation of the lower band here, we do not observe any superconductivity. Here you have an arrow. And we do not observe any superconductivity. Because the density of states for this band is too low just to induce the superconductivity in our system. Then we increase the chemical potential. Of course, this is the filling factor, chemical potential, or the gate energy. This is exactly the same. If we increase the chemical potential and we are exactly at the Lifshitz point, this Lifshitz point corresponds to the points in which the superconductivity is induced, because we have a state-like increase of the density of state here. So we have sufficiently high density of state just to induce superconductivity. And then the characteristic shape, in fact, is induced not by the interband repulsive interaction, but by the interplay between topology of the Fermi surface and the symmetry of the gap, which in our model we assume that it is extended S-wave. Okay? So, summing up my presentation, we have obtained a DOM-like behavior of TC, which is also observed in the experiment, and we explained that this characteristic shape can be induced by the extended S-wave symmetry of the gap realized in the system. Moreover, we showed that, in fact, the superconductivity is probably induced by pairing in the higher lying bands, dxz and dyz, and the Lifshitz transition is not exactly at the critical temperature, but the Lifshitz transition it's a point in which the superconductivity is induced. And this picture does not change if we include the Coulomb interaction, if we include the spin orbit interaction. So it seems that our theory is able to describe the characteristic shape quite well. Okay, but of course we are still waiting for the experimental results which are able to confirm that in this system we have the extended S-wave symmetry. Okay, thank you very much for your attention.
Thank you for a very nice talk. Please, if you look at the Hamiltonian attraction part of the Hamiltonian, did you analyze attraction part, not repulsion? The next. Yeah. Did you analyze just the physical origin of the parameters, the values of parameters from the first principle, for example, or are they just fitting?
Of course, in our model, the J is just a parameter.
Yeah.
So in fact, we just set J just in order to get the critical temperature here exactly the same as an experiment.
Okay, thank you.
So it is not very high, but the J prime is always one order of magnitude smaller, but this term guarantees that although in different bands we have a different energy gap, we still have exactly the same critical temperature for all.
Okay, I would like just to attract your attention that the physical origin maybe you told in conclusion that it's still under debates, under future investigation, and because we already published paper in 2016 in the continuum approach, we account for the electron-phonon interaction with interface or optical phonons of strongly polar substrate. I think it cannot be ignored. This model is a bit quite simplified, but I think we had some qualitative explanation, not detailed the shape, but I think it deserves some attention. Maybe it can contribute just to this Hamiltonian if you perform some transformation, some translation to this language from our continuum.
Thank you, Sergey. We understand. But where was it published, by the way?
In Journal of Superconductivity and Novel Magnetism.
Okay.
Proceedings of the previous conferences here.
Okay, thank you. Yeah.
I would like to thank for bringing my attention to this probably interesting paper, but maybe I should say something more. In fact, we know two different papers published in peer review about the possible dynamic mechanism in the system. One is based on electricity and domain and movement of the electricity domain, and the other one is about the fluctuations. But both of them suggest that, in fact, the symmetry of the gap in the system could be extended as well. And I have a question to you: that your theory is also able to just predict the symmetry of the gap based on this mechanism related to phonons, or?
Yeah, the main mechanism which we use just the electron-phonon interaction.
Okay.
Together with Coulomb, without any assumption of the strengths. So we account for the retarded character of the interaction and work beyond the adiabatic approximation for the effective interaction. But what was simplified, of course, we used we did not take into account this extension of the symmetry.